Welcome back, folks. Today we're going to be expanding on something we covered a little bit in the last lesson. That's going to be quadratic applications. Now, previously we'd learned how to determine the y-intercept and calculate the axis of symmetry and vertex. As we were talking about last lesson, any projectiles, so something like a rock, a basketball, a ball of any sorts, those all fly through the air on a parabolic curve. So we want to figure out the information that would be useful in determining the highest point, the time for the highest point, and the initial height. So the initial height is going to be our y-intercept. This is going to be our y-intercept, or that's going to be our c value when we're talking about this in standard form, ax squared plus bx plus c. What about the time at the highest point? Well, the highest point, the maximum or the minimum, is always the vertex. So the time at the highest point would be our axis of symmetry, or our vertex, just the x value of the vertex. And the highest point will be the y value of the vertex, because it's going to be the highest point reached at the highest time. And this brings us to the idea of projectile motion, or falling objects. In the real world, the function h is equal to minus 16x squared can be used to determine the height of an object at any time. Minus 16x squared, minus 16 would be the acceleration due to gravity in feet per second squared. H is going to be our height, and x is our number of seconds. But both our y-intercept and the vertex are 0, 0. So what does this tell us about the initial assumption of the height? It tells us that we're assuming we're starting from 0, 0. It assumes that we're starting from a height of 0. How could we change this to drop it from an initial height of c feet? Well, we'd want to have the point 0, c, which means we move our y-intercept up. And this leaves us with our standard function for position over time with a projectile. That's going to be h of x, our height, will be equal to minus 16x squared plus bx plus c, where c is going to be our initial height, and b is going to be our initial velocity, or our initial speed. All right, let's go ahead and get into a question, an example of this. We have a ball kicked from an initial height of 3 feet with an upward velocity of 20 feet a second. When will it be at its highest point, and what will the highest point be? So what's our equation going to be? H will be equal to minus 16x squared minus 16x squared. Our initial speed, or our initial velocity, was 20 feet a second. So we're going to be adding 20x. And what's our initial height? Our initial height was 3. So it's going to be h is equal to minus 16x squared plus 20x plus 3. When will it be at its highest point? Well, the time of highest point would be the b value, or our vertex. And the x value for our vertex was x is equal to negative b over 2a. Remember, this was the point for our axis of symmetry and the x value for our vertex. So this is going to be x is equal to negative 20 over 2 times a is negative 16. Throw that into a calculator, and you'll find out that our maximum time, or our height for our maximum time, will be 0.625 seconds. So our time is 0.625 seconds. What will our height be? Well, to find our height, all we're going to do is we're going to substitute in 0.625 for x. So we'll get h is equal to 16 times 0.625 squared plus, that should be negative out there, plus 20 times 0.625 plus 3. Let's go ahead and put this into our calculators. 0.625 squared plus 20 times 0.625 plus 3. And you'll find that the maximum height of this ball will be 21.75 feet. It's as simple as that. We're just trying to find the vertex, the x and the y values. The second problem is a little bit harder. Now we have Timmy hiking up to Fisher Point. He's curious how high the cliff is, so he drops a rock off. The rock takes 2.2 seconds to hit the ground. We're trying to figure out how high the cliff is. So let's ask ourselves, what is c? What is our initial height? Well, we don't know. That's what we're trying to figure out. It asks us how high the cliff is. Okay. What about b? What's our initial velocity? Well, if we're dropping the rock down, the initial velocity will be 0, because we have no initial speed. Let's put this into our equation. We find out that h will be equal to minus 16x squared plus 0x plus c. What else do we know here? We know that at 2.2 seconds, the rock hits the ground. Or in other words, at a time of 2.2 seconds, what is our height? Our height is at the ground level, or our height is 0. So we know we also have the point 2.2, 0. Now we have an equation and we have a point. From here, all we're going to do is substitute this point into this equation. Go ahead and do that and figure out what our value for c is, what the height is. So to do this, we're going to substitute in 0 for h. So we get 0 is equal to minus 16 times, instead of x, we'll have 2.2 squared plus c. And minus 16 times 2.2 squared is going to give us 0 is equal to minus 77.44 plus c. When we solve for c, we find that our initial height is 77.44 feet. One more problem. This time, we have someone standing on top of a building. He throws a snowball down at his buddy, who's standing on the ground. He throws the snowball with a speed of 10 feet a second, and it takes 3 seconds to hit the ground. How tall was the building? So again, what's our initial height? We don't know. That's what we're trying to figure out, because we're trying to figure out how tall the building was, or where the snowball was at the initial time. What about our initial speed? Our initial speed was 10 feet a second. But were we throwing this up, or were we throwing it down? If we were tossing it down, this needs to be a minus. So our answer is this is minus 10 feet a second. What's the last piece of information we have? Well, it takes 3 seconds to hit the ground. Or in other words, at a time of 3 seconds, our height should be 0. Let's go ahead and try to build our equation and see what we should do. Our equation is h is equal to minus 16x squared plus b is minus 10, so this is minus 10x. And we don't know what c is. C is our unknown. Now we have an equation and we have a point to the equation. Can we solve for c at this point? The answer is yes. So go ahead and solve for c. What's the initial height of the building? To solve for the initial height, we're going to substitute in 0 for h, and we're going to substitute in 3 for x. So this becomes 0 is equal to minus 16 times 3 squared minus 10 times 3 plus c. Or this will be equal to minus 16 times 9 minus 144 minus 90 plus c. And when we finish solving for this, we will find that c will be equal to 234 feet. Again, we can test this if we want by putting this in for this equation and seeing if we get 3, 0 when we substitute this in. So let's go ahead and try that. If we were to say h is equal to minus 16 times 3, or minus 144, minus 90 plus 234, h would be 0. So that turns out to be correct. Now this is the basis of the projectile motion for this. Always ask yourself, what's our initial height, what's our initial speed, and do we know any extra points? From there, you just substitute what you know into your equation, and then you try to solve for whatever is left. We have one other type of question, and that's quadratic regression. Earlier we talked about linear regression, substituting those values into our calculators and finding a line. This time we're going to be doing that with quadratics, because not always do things go up or down. One example of this would be something like the time and the heat, or the temperature. So let's go ahead and put these into your calculators. I'll meet you back there once we have these values in our calculator. For those of you who don't remember how we get to this list part of our calculator, we press the Stat button, and it gets us to an edit here. Once we get in there, we're going to put into L1 and L2, so we're going to delete any information we have inside both of those, and put in our new information. I'll come back to you when I have that in the calculator. And here we are with those values in our calculator. You'll notice that instead of going with times being 8 p.m. or 8 a.m., 10 a.m., and so on, we decided to use 8 a.m. as being our 0 hour and count each hour after that as being 2 hours or 4 hours and such. That'll save us from trying to have to figure out whether we're talking about 8 p.m. or 8 a.m. in the future. Now, how do we do a quadratic regression for this? Well, following the same steps for linear regression, we're going to hit that Stat button again. We're going to go to our calculator. And if you look under linear regression, you'll see there's one called quad regression, quadrig. And that's exactly what we want. We want quadratic regression. We're going to press Enter. If you've done this with L1 and L2, everything should be correct. So we can just enter our way through this and find our equation. This tells us that y will be equal to ax squared plus bx plus c, where a is this value, b is this value, and c is this value. And instead of r this time, we have r squared. So the r squared is a similar value of testing how good or how close these relations are. 0.99 is very close. So let's go ahead and write down our equation for this line. Here we have the equation for the line. Next thing our question asks us is, what is the temperature likely to be at 8 p.m.? How are we going to figure this out? Well, let's figure out what x value we want. At 8 p.m., that's going to be 12 hours after our initial start. So we're going to substitute in x is equal to 12 to figure out what our temperature may be. Let's go ahead and do that and put it into our calculators. So we get y is equal to minus 0.469 times 12 squared plus 7.216 times 12 plus 51.607. And when we put this into our calculators, that's 7.216 times 12 plus 51.607. We find that our temperature at 8 p.m. should be about 70.66 degrees Fahrenheit. And this makes sense. We saw our temperature peak at about 81 degrees and start declining. We're continuing to decline until we hit 70.66 degrees at 8 p.m. If we really wanted to check, we could also do a graph of these to make sure they were parabolic. However, if you're confident in that, all you need to know is how to do this quadratic regression. Alright folks, that is all we have for this lesson.